Welcome back to Basic Electronics. We have looked at some basic description of the BJT in the last class. We will now consider a simple BJT circuit and see how we can obtain the solution, that is currents and voltages. We will then see how the BJT can be represented for generalized bias conditions using the Ebers-Moll model. We will get started with the Ebers-Moll model in this class and see how it can be used to obtain the BJT IV characteristics in the next class. Okay, let us begin. Let us apply what we have learned so far to this simple BJT circuit. Here is a transistor and it has got a beta of 100. How do we know whether it's a PNP transistor or an NPN transistor? First, there is an arrow here. That means this node is the emitter. The arrow is coming out of the device. So that means there is a PN diode over there. So this node must be P and that one must be N. And if the emitter is N, the collector is also N type, and so we have NPN transistor. Of course, this is all right for the first time. Later, as we get used to transistor circuits, we won't really need to do all this jugglery to find out whether it's an NPN transistor or PNP transistor. Arrow coming out, it's an NPN transistor. Arrow going in is a PNP transistor. There are two voltage sources in this circuit. One is called VBB, and that is because it's going to the base terminal, and the other voltage source is called VCC, and that is because it's going to the collector terminal. Now these voltage sources have been shown explicitly, and in electronics it's a good practice, it's a common practice not to show these voltage sources explicitly, because it just makes the circuit diagram cumbersome. And therefore what is done is a reference node or ground is taken, such as this node, and with respect to that ground we say VBB is 2 volts here and VCC is 10 volts here. So that is 0 volts. You go up like that, you get 2 volts. You go up like that, you get 10 volts. Now for simplicity, for clarity, in this particular circuit we will show this NPN explicitly, but as we get used to transistor circuits, we don't really need to do that. Next, we replace the transistor with its equivalent circuit, assuming that the transistor is operating in the active mode. So let us do that, and that is what we get. So the rest of the circuit remains the same, and the transistor has been now replaced with this rectangle here. And what do we have inside? Between the base and emitter we have this diode, and between the base and collector we have the controlled current source that we have seen before. And if this current is IE, then the collector current is alpha times IE. And now we can proceed and obtain the solution for this circuit. Let us see how to do that. Since the BJT is assumed to be in the active mode, this diode is forward biased, and the voltage drop between B and E is VBE equal to 0.7 volts. And in the active mode we can also say that IC is alpha times IE, and that is the same as beta times IB, as we have shown earlier. And Therefore, if we know this voltage drop, we know that this is 2 volts. So 2 minus 0.7 is 1.3 volts. So 1.3 appears here, and 1.3 divided by 100K gives us the base current. So that is what this equation shows, and that turns out to be 13 microamps. Once we know the base current, we can calculate the collector current. So the collector current is beta times IB, that is 100 times 13 microamps, or 1.3 milliamps. What about the collector voltage here or here? It is 10 volts minus collector current times RC, this voltage drop here. So 10 volts minus 1.3 milliamps times 1K, that turns out to be 8.7 volts. So let's get the complete picture now. This is 2 volts. This voltage drop is 0.7 volts, but this is at 0, so this is at 0.7 volts, the base, and the collector is at 8.7 volts. So now we know the voltages at all terminals of the BJT. Now let us go back and check whether our assumption of active mode is correct. And what is active mode? The base emitter junction is forward biased, and we have already made that assumption. And the base collector junction should be under reverse bias. So we need to basically check now whether the BC junction, the base collector junction, is indeed under reverse bias with the values of voltages that we have obtained. What is VBC? VB minus VC. VB is 0.7 volts as we saw before, VC is 8.7 volts, and so the difference between these two is minus 8 volts. So that means the base is at a negative potential compared to the collector, and therefore this PN junction is under a reverse bias. So that verifies that our assumption of active mode is indeed correct. And so everything is consistent, and the solution we have obtained would make sense. Let us now consider the same circuit but with a slight change. We have changed RB from 100K to 10K now, and now we want to see what the solution is, the collector current as well as the various BJT voltages. So let's repeat the procedure that we followed in the last slide. First, assume the BJT to be in the active mode again. So we have VBE equal to 0.7 volts and IC equal to beta IB. No difference, same as what we saw earlier. IB is of course different now because our RB is different. IB is VBB 2 volts minus 0.7 divided by 10K. This was 100K earlier, now it is 10K. So it's 2 minus 0.7, 1.3 divided by 10K, which turns out to be 130 microamperes. Once we know IB, we can calculate IC, that is beta times IB, or 100 times 130 microamps. So that happens to be 13 milliamps. Now the collector voltage, the voltage at this node, is VCC 10 volts minus IC RC. So 10 minus 13 milliamps times 1K. It now turns out to be negative, minus 3 volts. Does this make sense? Let us see. What is VBC then? VB minus VC. VB is 0.7 volts because we have assumed this diode to be conducting. And VC, as we just found out, is minus 3 volts. So VB minus VC is 0.7 minus minus 3, or 3.7 volts. So VB minus VC is 3.7 volts. So this junction is now under forward bias. which is of course not the condition we require for the active mode. So something is definitely not right. So VBC is, first of all, it's positive and it is huge. No diode is going to uh, tolerate that kind of large voltage, because the current would just be hundreds of amperes, and that's not possible. So the solution we have got is not correct. And so what went wrong? What went wrong is our assumption of the BJT being in the active mode was not correct. So the BJT cannot be in the active mode, and therefore we need to take a second look at the circuit. So we'll come back to this circuit after we cover the BJT IV characteristics. We have seen so far the active mode of the BJT, both PNP and NPN. Here is a PNP transistor, for example. And what happens in the active mode? The base emitter junction is under forward bias, so that we replace with a diode. And the base collector junction is under reverse bias, and we put a current controlled current source over there. And if this current is IE, that is alpha times IE, and alpha is close to 1, little less than 1. Now if we look at this transistor, we realize that there is a diode there, there is also a diode there. So there is also a reverse active mode possible, and that is shown here. What does that mean? That means this base collector junction is under forward bias, and this junction, the base emitter junction, is under reverse bias. So that's another possibility. And now what we do is, since this is under forward bias, we put a diode there, and since the base emitter junction is under reverse bias, we put a current controlled current source there. If this current is minus IC, this current is alpha R times that current, as shown there. And note that we have continued to use the same terminal names, so collector here, although this terminal is now acting as an emitter, because that is under forward bias. So there is an alpha associated with this active mode, or more appropriately the forward active mode, and there's also an alpha associated with the reverse active mode, this alpha, and this is called alpha F, or very often simply alpha, and this is called alpha R. Alpha F is also called the forward alpha, alpha R is called the reverse alpha, and they are generally quite different, because as we mentioned earlier, the base emitter junction and the base collector junction are very different from each other. The doping densities are not symmetric, and therefore these two alphas are generally quite different. Typically alpha F is much closer to 1, for example it could be greater than 0.98. Alpha R is small compared to 1, and it could be as small as 0.02. And as a result, the corresponding current gains, beta F corresponding to this alpha F, and beta R corresponding to this alpha R, they also differ very significantly, since beta is alpha over 1 minus alpha. In amplifiers, we don't normally bother about this reverse active mode, because the reverse beta is so poor. So in amplifiers and many other analog applications, the BJT is biased in the forward active mode, or it is simply called the active mode. We don't often mention this word forward, and that is done because we want to make use of the higher value of beta in the forward active mode. So to summarize, the transistor is capable of operating in the reverse active mode, but in most applications we don't operate the transistor in that mode because the alpha R value is poor and therefore the beta R value is poor, and therefore the performance of the circuit if the BJT operates in the reverse active mode would be very poor. And that brings us to the Ebers-Moll model for a PNP transistor. We will only consider the PNP transistor to begin with, and later we will see that the Ebers-Moll model for an NPN transistor is very similar, and once we understand the PNP transistor model, it is almost trivial to get the model for the NPN transistor. Alright, now before we begin, let us look at the direction of these currents once again, that is IE, IC and IB. An easy way to remember these directions is to connect these directions with the BJT in the active mode. And what do we have in the active mode? We have the emitter base junction forward biased and the base collector junction reverse biased. Now if this junction is forward biased, then the current that will flow would be in that direction, and that is the same direction as the emitter current here as well as here. The collector current essentially is in the same direction as the emitter current. So if the emitter current is like that, the collector current is also like that. And the base current is in the same direction as the collector current. If the collector current is coming out of the device, then the base current is also shown as coming out of the device. Another way to look at it is in the active mode, all these currents are positive, and that will happen if the base current is shown to be coming out of the device. Let us see why. As we have seen earlier, IC is alpha times IE in the active mode, and alpha is slightly smaller than 1. Therefore, IE minus IC is a positive current, and that essentially comes out as the base current. So these currents here, IE, IB and IC, are reproduced in this figure, IE, IB and IC, in the same direction as in the first figure. And now we come to the Ebers-Moll model. The top branch here corresponds to the active mode, and the bottom branch corresponds to the reverse active mode. And let us consider the active mode first. In the active mode, the base emitter junction is under forward bias and the base collector junction is under reverse bias. And in that situation, D1 will conduct and D2 will not conduct. So this current is very small. So this branch is as good as an open circuit, and since this current depends on IC prime, this is also an open circuit, and we are left with the diode here and the dependent source here. And in that case, IE and IE prime will be equal. IC and alpha F or alpha times IE prime will also be equal, and that is exactly the model we have considered for a BJT in the active mode. Similarly, in the reverse active mode, the base collector junction is under forward bias and the base emitter junction is under reverse bias, and therefore this current now will be negligibly small, and therefore the D1 branch as well as this current controlled current source would be open circuits. And now we are left with D2 and this dependent source. And now IC is minus IC prime, IE is minus alpha R times IC prime. So that accounts for the forward active mode, or simply the active mode, as well as the reverse active mode. Apart from that, we have two other situations. One in which both of these diodes are under forward bias, and another in which both of these diodes are under reverse bias. Now the nice thing about Ebers-Moll model is that it can be used for all of these modes of operation, as we will see. Next, let us look at what IE prime and IC prime are. These currents are given by the Shockley equation. For D1, we need to take VEB as the diode voltage, and for D2, we have to take VCB as the diode voltage. And when we do that, we get these equations. IE prime is IES, this is the reverse saturation current for D1, and it has got this subscript E because that's close to the emitter. S is the reverse saturation, so IES times exponential VEB by VT minus 1. So it's exactly the same as the diode equation we have seen before, except V is now VEB. These currents IES and ICS are very small, a picoampere or even smaller, and in normal operation this small current would get multiplied by this large exponential factor, and therefore we can get reasonable currents. So now we have the complete model. Let's say we know VE, VB and VC, the three terminal voltages. Then we can calculate VEB as well as VCB. Once we know those voltages, we can calculate IE prime. This is just a number which is known for a given transistor. VT is the thermal voltage, about 25 millivolts at room temperature. So all of these things are known as soon as we know the terminal voltages. So we can calculate IE prime as well as IC prime. So we have this current, that current. If we know this current, we know this current as well, because alpha F is also known. If we know IC prime, we know this current as well. And so we know all of these four currents, and we can then write a KCL at the base node to obtain IB. Here are the various modes in which the transistor can operate in, and there are four modes because we have two junctions. Each one can be forward biased or reverse biased, so that gives us four combinations. We have already seen the forward active mode. We have in fact also seen a circuit example of this mode. In the forward active modes, simply called the active mode very often, the base emitter junction is forward biased, base collector junction is reverse biased, and because of that IE prime, this diode current, is much larger than IC prime. For all practical purposes, we can say that IC prime is 0 in this case. Then there is the opposite case, the reverse active mode, in which the base emitter junction is reverse biased and base collector junction is forward biased. And in this case, just the opposite happens. This current is non-zero and IE prime is 0 because D1 is under reverse bias. And these are the other two modes we have not seen so far. There is a mode called saturation. In that mode, both of these junctions are under forward bias. So the base emitter junction is under forward bias, base collector junction is also under forward bias. And because of that, both IE prime and IC prime are now substantial, and they may even be comparable. In the fourth mode, the cutoff mode, both of these junctions are under reverse bias. IE prime is 0, IC prime is 0, this current is 0, this current is 0. Essentially all currents are 0 and the transistor looks like an open circuit. from any of these terminals. So that is the cutoff mode. And as we said, the Ebersmol model can be used for any of these modes, and that's a very attractive feature of this model, and is therefore commonly used. In circuit simulators, there is another model which is a little more advanced, but essentially the idea is similar, that the model describes all of these modes in a nice comprehensive manner. That's called the Gummel-Poon model. For our purposes, the Ebersmol model is definitely adequate, and we will see the results that we get from this model. Here is the summary of what we have said about the Ebersmol model, and we also show the NPN Ebersmol model in this figure. For the PNP transistor, the emitter current is into the device, the collector current is in the same direction as the emitter current, and the base current is out of the device. And if we write KCL, we get IE equal to IB plus IC with all plus signs. In this case, we talk about VEB as the forward bias for D1, and therefore that is the voltage that enters the equation for IE prime. For the other diode, for D2, we talk about VCB as the diode voltage, and that is the voltage that enters the equation for IC prime. For the NPN transistor, we show IE as flowing out of the device, and it's easy to imagine why it is out of the device. Under active mode, we have a PN diode there under forward bias, and that forward biased diode is going to allow current only in that direction. So that is the direction of IE. IC is in the same direction as IE, and IB is going into the device. And once again, if we write KCL, we will get IE equal to IB plus IC with all plus signs. The Ebers model for the NPN transistor is here, and as we see, it's very similar to for the case for the PNP transistor, except now we have this polarity of D1 and D2 reversed, because earlier we had PN here, now we have PN like that. So therefore the polarity of D1 is reversed as well as the polarity of D2. The IE prime current is now marked in the other direction, because we expect this current now to be positive when D1 is under forward bias. The current controlled current source here is also in the opposite direction, essentially the same direction as IE prime. So this is still given by alpha F times IE prime. Similarly, IC prime is in that direction, because that is the direction in which the current will flow if D2 is under forward bias. And the other current controlled current source also is in the same direction as IC prime. And what about the base current? The base current can be obtained once again by writing the KCL equation at this node. These two nodes of course are the same, and so are these two. IE prime is now given by this equation. It's very similar to the PNP Ebersmol equation, except we have VBE now, and the reason is simple, because this diode is forward biased if VBE is positive. That is why we have VBE here. Similarly, in the IC prime expression, we have VBC here and not VCB. So things are definitely very analogous in these two cases, and we don't really need to remember any of these. We can actually just sit down and draw these models on paper, and that is what this stop sign is saying. So stop watching the video, take a break, take your pen and paper, and draw these Ebers-Moll models for the PNP transistor as well as for the NPN transistor. Once you are finished with that, come back and check if you got everything right, and then we will proceed further. Let us now look at the Ebers-Moll model in the active mode, and we have commented on this earlier, but let's just put it down once again because it's so important, and we'll do that for both PNP and NPN transistors. In the PNP transistor, what is the meaning of active mode? That means D1 is forward biased and D2 is reverse biased. So therefore this current is very small, and we can treat that as an open circuit, and that's why it appears in a light color. If this IC prime is small, alpha R times IC prime is also small, and therefore that is also an open circuit. Then the Ebers-Moll model boils down to D1 and this current controlled current source, and that is exactly what we considered earlier. Same thing for the NPN transistor. D1 is under forward bias, D2 is under reverse bias, so this current is negligibly small. So is this current, and therefore we are left with D1 and this current controlled current source. And now in both of these cases, this IE becomes equal to IE prime, and IC becomes equal to alpha times IE prime, and that's the same thing here, except for the directions of the current. IE and IE prime are the same, and IC and alpha IE prime or alpha IE are the same. So this slide only shows that the Ebers-Moll model does reduce to the BJT model in the active mode that we considered earlier. So it's a special case of the Ebers-Moll model. And whenever we come across a BJT in the active mode, we can conclude that the base emitter diode has about 0.7 volts across it. It's conducting in the forward direction, and the collector current is alpha F times IE. Alpha F is often just called alpha, and as we have seen before, that is the same as beta times IB. And these relationships hold both for the PNP transistor and the NPN transistor without any negative signs, provided we denote our currents as shown here. To conclude, we looked at a simple BJT circuit in this class in which the transistor operates in the active mode. We found that changing one of the resistance values gives results which are not consistent with the assumption of active mode. Clearly, in this case, the BJT is operating in some other mode. To handle situations like this, we need a BJT model which can be used in all modes of operation. The Ebers-Moll model is one such model. It is relatively easy to understand and is also reasonably accurate. Using the Ebers-Moll model, we can describe the BJT behavior completely, as we will do in the next class. So see you next time.